because I want to finish the all the slides first today. So inshallah afterwards I will share with you these complete slides. Okay. So we continue regarding the method for accounting loss, methods of accounting for component loss in a gas turbine cycle. Okay. So before this, we have seen two methods, which is the first one regarding actually not methods, factors, factors affecting component loss. Okay, the first one was the regarding the stagnation properties or the total properties. Remember the total temperature, total enthalpy, the energy values. Okay, and this leads to the compressor and turbine efficiency. Okay, so the loss in the total properties values will lead also to energy loss somehow in the compressor and turbine efficiency. So we have seen that, and then today we will continue. So there are around 5, 6 another factors or methods that accounts for this cycle component loss. Okay. So the third one is the pressure loss. Okay, so this one usually occur in the heat exchanger, combustion chamber here for gas turbine and aircraft. It is in combustion chamber. So a loss in stagnation pressure, we note it as here in the burner B, usually the burner of the combustion chamber. So the loss, the change in the pressure entering and exiting the combustion chamber or the burner. Okay, so due to the resistance, flame stabilizing, mixing device, etc. Okay, and also due to the momentum change produced by exothermic reaction. Exothermic reaction is the chemical reaction, the chemical reaction in the combustion process. Okay, so due to those, so this leads to the pressure loss during the combustion process, the process in the heat exchanger. Okay, so there is also sometimes frictional pressure loss in the passage. Okay, frictional pressure loss within the at the air side, the working fluid air, or at the hot gas after the mixing of fuel and air. Okay, so there will be some frictional pressure loss as well. Okay, so if you look at the figure of the cycle, TS diagram, again temperature versus entropy diagram. Okay, so the pressure loss have the effect of decreasing the turbine pressure ratio relative to the compressor pressure ratio, and thus reduce the net work output from the plant. Okay, so if you look at the cycle here, the thermodynamic cycle here of a gas turbine cycle with, okay, if you remember from last week, previous class, okay, so this cycle is with what we call a regenerator or recuperator. Okay, regenerator or recuperator. Okay, nampak. Okay, so if you look at the first part, this one from 1 to 2, so that is the compression process. Okay, accounts for compression process. So the from 1 to 0 to, or the stagnation properties to pressure to. Okay, that is the ideal process, the vertical line. It means that there is no any loss. Okay, it means if the efficiency is ideal. So we have the process is isentropic, we call it. Means there is no energy loss. Okay, no entropy loss. But somehow in the real process, it's actually from 1 to 2. It is a bit there is a slightly difference in entropy. So when there is difference in entropy, means the process is irreversible. Okay, so it's not ideal. Okay, so from in the pressure loss inside the combustion chamber is from 2 to 3. Okay, 2 to 3, the combustion process. So if there is this difference in pressure, okay, so the process in the combustion chamber will not be at constant pressure anymore. Okay, remember in the ideal case, ideal cycle, we assume that the process in the combustion chamber occur isobar, means constant pressure. But in real case, there is somehow somewhat a pressure loss. Okay, here. So that's why the isobar line, the curve this way. Okay, that is the isobar line in the this thermodynamic diagram. Okay, so the pressure will we assume that the pressure here, the stagnation pressure at the third state is less. Okay, loss due to the those factors just now, friction, etc. So the PO3 will be less than P2 before the process. Okay, so there is example of pressure loss in the combustion chamber, and thus effect of decreasing the turbine pressure ratio relative to the compressor pressure ratio, and thus reduce the net work output from the plant. Okay, so if the P pressure 3, the total pressure at point 3, state 3 means exiting the combustion chamber. This here, this is this one combustion chamber, and as it just before entering the turbine. So if total 3 pressure is less, it means decrease, so thus the net work output, which the work produced by the turbine expansion process, and minus the work used by the compressor. So this net work output will decrease as well, because the pressure at the inlet of the turbine, PO3, is decreasing. Okay, so that is one thing. Uh, and thus reduce the network output from the plant. Okay, so this is how we calculate okay, the pressure loss. So the fixed value of the loss, okay, the fixed values of the loss can be fed into the cycle calculation directly. Okay, so for a simple cycle with a regenerator just now, heat exchanger regenerator, so the turbine pressure ratio, the PO3 over the PO4, inlet over outlet for turbine, okay, can be determined from, okay, so the PO3 will not be equal to total 2 PO2 anymore. So we have to take into consideration those difference, the loss. The loss will be given sometimes if in percentage, or in a total value of loss. Okay, so PB, the loss in the during the combustion process, and PHA, the loss at the air side just now, hot fluid just now. This one also there will be some loss of pressure, and at the gas PHG, at from the hot gas side also, there will be a pressure loss. So we have this calculation, okay, to calculate the new value of pressure inlet and outlet of the turbine. Okay, PO3 and PO4. Okay, and then okay, and then pressure loss again. So the same calculation just now, we can also rewrite it in terms of this, just to link the PO3 with PO2 in inlet and outlet of the combustion chamber. So we can also, so it is the same as the equation just now previously. It's just that here we can link the function with PO3 is function of PO2, depends on the PO2 inlet of the combustion chamber. Okay. And then what else? Okay, so the pressure loss can be minimized by using a large combustion chamber with consequent low velocity. This is actually if you think about Bernoulli principle, or something that if the pressure and the velocity always opposite proportional. Means if we from the Bernoulli principle of fluid mechanics, if we minimize this pressure loss, then the velocity combination with consequent low velocity. The pressure loss can be minimized by using a large compensation chamber with consequent low velocity. So the velocity will be decreased as well. Okay, and then typical values of PB, the pressure loss just now. Okay, the pressure loss in the burner will be about 2 to 3% for a large industrial unit and 6 to 8% for an aero engine. Okay, this just example. And then okay, so that is about the one of the factor which is a pressure loss occurring in the combustion chamber or in the heat exchanger. Okay, so another factor is the heat exchanger effectiveness. Also, it is like the efficiency of the heat exchanger, because it's just that we call it as effectiveness, but the meaning behind is like the efficiency of the compressor turbine. So it is the efficiency of the heat exchanger. So heat exchanger has the effectiveness of the heat exchanger. We can account it in take into account this heat exchanger effectiveness. Okay, so heat exchanger for gas turbine can take many forms. Okay, so if you use a recuperator or regenerator, okay, recuperator where the hot and cold stream exchange heat through a separating wall, means we recuperate, we reuse the heat from the hot side, the hot stream, and kind of like give it to the cold stream. So exchange heat, hot and cold, use the hot side fluid stream and exchange it with the cold side. Or regenerator where the streams are brought cyclically into contact with the matrix, with alternately absorbs and rejects it. So actually the function of recuperator, regenerator somehow kind of like the same. Okay, so this one. Okay, so we use the heat. This is the ideal case of simple gas turbine with heat exchanger with a regenerator. Okay, so we use the hot feed from the hot side and we use it to preheat the air, the working fluid after exiting the compressor. Okay, so we add another heat exchanger. Okay, so this the fundamental process is that the turbine exhaust gas reject heat at the rate of okay. So T4, 4 and 6. Okay, so this is the same diagram at the beginning, not at the beginning, during the simple gas turbine cycle with the regenerator. Okay. So using the same diagram for 6. Okay, for 6 are the hot side. For 6, okay, the fundamental process is that the turbine exhaust gas. Okay, turbine exhaust gas reject heat at the rate of the MTCP, etc. Those are the enthalpy. H, the energy. Enthalpy is energy in joule. Okay, the enthalpy, the heat. Okay, energy, heat also is a form of energy. So the rejected heat from the exhaust gas means exiting the turbine. Okay, 4 to 6 just now. Okay, so this rate can be calculated as MC, mass, CP, specific heat, and the change of the temperature. While the compressor delivery air receive heat at rate of MCP, T05, T02. So actually, what does the sentence means is that the exhaust gas, okay, exiting the turbine here, Okay, at state 4, location 4, position 4. So the exhaust gas will reject heat at the rate just now, MCP just now, and will give the deliver the heat to the after the compressor 2 to 5. Okay, so that is why we have this relation in equation 2.21. Okay, due to the conservation of energy, so we assume that all the energy from the hot side 4 to 6 just now will be transferred, exchanged to the cold side to preheat the air after compressor. Okay, 2 to 5. So from the conservation of energy law, we assume that the those energy, those heat rate, okay, CPT, etc., balance the same, are equal. Okay, means conserve what is given and what being received is the same. Okay, but both T05 and T06 are unknown and second equation is required. Okay, as this, if you want to solve this type of equation, this equation, we need to have the value of TO5, which is TO5 just now is the temperature, the total temperature or stagnation temperature exiting the regenerator from the cold side, from the cold side. And TO6 is the temperature exiting the regenerator but from the hot side. Okay, so normally those values are unknown, so that's why we need a second definition equation to solve it. Okay, so this is provided by the equation expressing the efficiency of the heat exchanger. So that's why we need another expression, okay, another equation that characterize the effectiveness just now, the effectiveness of the heat exchanger. Okay, so now the maximum possible value of TO5 is when the cold air attains the temperature of the incoming hot gas. Okay, so if a TO5 equals to TO4, and one possible measure of the performance is the ratio of the actual energy received by the cold air to the maximum possible value. Okay, normally we will use the second part, the second phrase. Okay, the ratio of the actual energy received by the cold air to the maximum possible value. Okay, so so this is this equation below is the one of the equation of the effectiveness of the heat exchanger. So actually we the real process, which is 2 to 5 just now, over the denominator is the maximum possible heat exchange, the rate of heat being exchanged. Okay, 2 to 4. 2 to 4. If we assume the maximum, means from the minimum to highest to the highest point, which is point 4 here. Okay, so that is the the maximum possible value that the heat exchanger can transfer the heat. So the this ratio is the effectiveness of the heat exchanger. Okay. And then, okay, so the mean specific heat of air will not be very different over the two temperature range. So thus we have this equation 2.24. So we just cut out the if the mass NCP constant specific heat and the mass maintain the same. So so we only left with the temperature value TO5 minus TO2 and TO4 minus TO2. Okay. And then again, for heat exchanger effectiveness, when the value of effectiveness is specified, equation 2.222 just now, and numbers the temperature and inlet to the combustion chamber to be determined, then needs to okay, this is how the steps that we can use to calculate. Okay, but so later on we will look at the example of a gas turbine. Okay, we will see how do we solve this type of relation. Okay. Uh, The larger the volume of the exchanger, the higher the effectiveness, but is limited to heat transfer surface area. Okay, so these are the limitation of the heat exchanger. So of course, heat exchanger first depends on the surface area. Okay, normally the higher the surface area, the higher heat can be exchanged. Okay, between those substance, those contact, those fluid. Okay, turbine exit and inlet temperature fixed by the material used. Okay, there is also constraint from the temperature, the maximum temperature, the fixed temperature of the turbine, and then thermal stress during startup, hence not suitable for frequent starts are required. Okay, so this is part of the heat exchanger effectiveness. Okay, and then other factors are mechanical loss. Okay, mechanical loss. In gas turbine, the power necessary to drive the compressor is transmitted directly from the turbine without any intermediate gearing. Okay, any loss that occurs is therefore due only to bearing friction and windage. This loss is very small and it's normal to assume that amount to about 1% of the power necessary to drive the compressor. Okay, so normally in ideal case, we assume that all the power produced by the turbine it will be used to pump the compressor to compress. So WT work or the power equals to WC. But somehow actually there is some mechanical loss. So that's why we need to take into account this loss. Okay, so by adding again and if there is another efficiency noted as mechanical efficiency. So actually the the wait, sini. So, okay. I think that one. Kita balik. Okay. Then, okay, sorry, terbalik. Okay. The efficiency should be at the turbine part, if I'm not mistaken. Okay. So actually the work used by the compressor is less than the actual work produced by the turbine. So due to the mechanical loss. Okay. This one, mechanical loss. If the transmission efficiency is denoted as eta M, the mechanical loss efficiency, we have the work output required to drive the compressor given by. So we can also write the equation, the expression to take into to take into account this mechanical loss. But normally, this mechanical loss is very small, around 1% just now. So the efficiency will be 0.99%, 99%, 99%, 0.99 with that percentage. Okay, so the work driven that drive the compressor. So instead of having just CPT, okay, the calculation of the work, so we need to take into consideration this mechanical loss, this transmission efficiency. Okay. And then other factors is the variation of the specific heat. Okay. So before this, we always assume that the specific heat CP, remember CP is in joule per kilogram per Kelvin. Okay, so it is the amount of heat energy that we need to be given to the compressor or to the device. The energy need to be given per kilogram, joule per kilogram per kilogram in order to raise 1 degree of temperature. Okay, so the unit is CP Okay, CP again, CP or in kilojoule or in joule per kilogram Kelvin. Okay, so the rate of energy, the amount of energy per kilogram in order to raise 1 degree of temperature, Kelvin or Celsius. Okay, and then gamma, again, gamma is the specific ratio. So gamma has no unit, it is dimensionless. Okay, so this both of these properties, in ideal case, normally we assume it as a constant value. So for air, CP for air is around 1005 joule, or around 1000, 1005, 1002, something like that. Okay, 1005. Okay, joule per kilogram Kelvin for air. And gamma for air, normally we take it as 1.4. Okay. But this those values is actually they are not constant. Okay, in real, of course, they are not constant. They change, especially depending on the temperature. Okay, depending on the temperature, the values of this specific heat can be changed. Okay, so because due to the dynamic movement of the fluid, of the gas. Okay, so actually in order to really take into account the performance of the cycle, we need to consider actually that this CP varies, okay, according to the temperature. So normally there is some sort of a correlation expression, but depending on the type of fluid, depending on the process. So CP, if you look at some article regarding this gas turbine cycle or aircraft engine cycle, so sometimes they define use some correlation for this CP depending on temperature. Okay. But usually in our calculation, we have like a fixed number, 1005 or 1200, it will be given. Okay. The same is true to gamma. Okay, gamma just now. And R, R is the gas constant. Okay, so gamma also change. Sometimes is usually is 1.4 for air, but if it's being mixed after the combustion process, the air will be mixed with the fuel. Okay, so the combination of the this air and fuel normally will have a gamma, the specific ratio around 1.33. So kalau if for air, we take it as around 1.4. For after the combustion, air plus fuel, the mix of this fluid will be, the gamma will become around 1.33. So the gamma change as well, because as you can see, this gamma depends on CP, gas constant, and since this specific heat depends on the temperature, so if specific heat change, then gamma also will change value depending on the other parameters. Okay, this one tak apa kot. Okay, so this is like diagram figure links the CP and gamma with the temperature. So you can see if we change the temperature, high temperature will have higher CP, specific heat, in kilojoule per kilogram per Kelvin at the left hand side, okay, y-axis. And then gamma, however, will decrease if we increase the temperature. Okay. And then variation of specific heat, CP increase, gamma decrease, etc. And this is the value of R, the gas constant. So ada banyak parameter, tapi tak apa, tak perlu hafal pun. Tapi from time. Usually bila kita banyak kali guna nanti dia akan hafal lah insyaAllah. Okay, tapi tak perlu hafal. So R constant is 0.287, the gas constant, or 287 kilojoule per kilogram Kelvin. Okay, so R also linked with the Cp and gamma, specific heat. Okay, this one. Okay, so this is example for air and the gas, the fluid after the combustion, after mixing the fuel with the air, the working fluid. So we have a Cp air 1.005 kilojoule. In kilojoule is 1.005. If it's in joule, so 1005 kilogram per Kelvin, and gamma for air is 1.4. Okay, or combustion gas. After the combustion gas, we have Cp of the gas, the mixing gas 1.148 or 1.15, and gamma will become 1.33. Okay. Okay, another two factors are fuel to air ratio, combustion efficiency, and cycle efficiency. Okay, fuel to air ratio. Okay. The performance of the cycle can be expressed in terms of the SFC. SFC is specific fuel consumption, or sometimes we is written as a TSFC, especially for aircraft engine. TSFC is the thrust specific fuel consumption. So it is the ratio of the fuel, the mass flow rate of the fuel, or the fuel to air ratio over the thrust power, the power produced. Okay, so but in gas turbine cycle, usually it will be between the ratio of the fuel to air ratio to the network output produced. Okay, fuel mass flow per unit net power output. Okay, since the process is adiabatic with no heat transfer, adiabatic means no exchange heat, okay, between the system, or the device to the outside environment. Okay, the energy equation is simply okay. So so we can use this one, this expression, that link the actually this expression is derived from the energy balance 2 to 3 is within the combustion chamber. Okay, the energy balance. So we know that the energy conservation of energy is conserved, inlet and outlet. So from there, from the conservation of energy, we derive this expression. Okay, I'm not going to do the mathematic derivation. So just explain how do we get this expression. It is from the conservation of energy, means the energy inlet and outlet of the combustion chamber from 2 to 3, the location 2 to 3 just now. Okay, so since there is no heat transfer, so there is no work, there's no Q, the value Q heat transfer. So that's why we only have this enthalpy. Okay. So where M is the product I per unit mass of air, and HI is enthalpy. Okay, so if you have actually this expression, if you have several mass transfer within the closed system, kalau ada banyak keluar masuk dia, kan, so that's why ada I, ada product I. But usually if there is only one, so just neglige the I. Okay, so means that the equation is just MH total 3 minus H total 2 plus F HF. Okay. Making use of the enthalpy of fraction at reference temperature of 25 degree delta, the equation can be expanded into become, okay, so if you want to modify the equation, when CPG is the mean specific heat temperature range, okay. Okay, this one tak apa lah, dia lebih pada chemical reaction. So the combustion, okay, this diagram we actually can be used, this figure 2.15, combustion temperature rise versus the fuel to air ratio. So we can use this diagram for gas turbine cycle. So it means that from here, if you know the inlet air temperature during the combustion process, and we know the temperature rise, the temperature difference within the combustion chamber, okay, process. So we can use this diagram to search to know the fuel to air ratio. Okay, so if you have the inlet air temperature of the combustion is around maybe 700 Kelvin, okay, and then the temperature rise due to the combustion process around 300. So we can use these figures. It's not very clear, but it's okay. Okay, 300 and 700 of the inlet air temperature. So from here we get the value of F. Okay, 0. Maybe 0.0083, something like that. Okay, so we can use this value of fuel to air ratio that we get from this diagram. Okay, and then what else? I talked on the session that the fuel is completely burned. The most convenient method of allowing for combustion loss is by introducing. Okay, so combustion efficiency. Another efficiency, so ada banyak efficiency. Okay, another efficiency to account for the loss of the combustion process. Okay, so but the definition, the general definition of efficiency stay the same. So it's theoretical ideal over actual. Okay, so just remember ideal over actual. So it's okay. Okay, so just so combustion efficiency is the theoretical of F, fuel to air ratio just now, over the actual F, fuel to air ratio during the process. So that is the combustion efficiency or burner efficiency. Okay, the efficiency of the combustion process. Okay, and then apa lagi cycle efficiency. Okay, specific SFC just now. Okay, so once the fuel to air is ratio is known, okay, once we have this value, and where M is the air mass flow and the specific efficiency can be found from, so we can calculate, we can measure the SFC. Okay, using this expression, is the fuel to air ratio over the net work output from the cycle. Okay, network output means work turbine minus the work used in the compressor. So since the fuel consumption is normally measured in kilogram per hour, while net work output is in kilowatt per kilogram per second of airflow, the SFC in kilogram is given by the following equation. So okay, this we can change the unit. Okay, the unit used for a specific fuel consumption. So just multiply with 3,600 just now. Okay, to change the unit from second to hour. Okay, otherwise it is still correct if we just calculate the CFC in this form, fuel to air ratio over the network output. Okay, in the gas way, it's not possible to utilize the latent heat. Okay, so tambahan. Okay, and another thing. Okay, this is the cycle thermal efficiency actually. Okay. So for this one, you can see here is actually the SFC just now. This part is the SFC. So you just divide by the Q net. This Q net is the heating value. Heating value of the fluid, of the gas. Okay. So usually it is also a constant value given. So normally it is around 41,000 kilojoule per kilogram for the fuel that we use. Okay, so this Q we call heating latent, some notations like that. Okay, so sometimes it's around 41,000 kilojoule per kilogram or 42,000 kilojoule per kilogram. Okay, so this is to calculate the cycle thermal efficiency. So we need to take into consideration the this heating value, okay, which depends on the type of fluid used, the gas. And then okay, so here is given 43,100, so around 40,000. Okay. Okay, last one, the factors accounting for component loss. Small thing. Okay. Okay, bleed flow. So bleed flow, so turbine unit temperature are limited by metallurgical consideration. We know that we have a constraint, which is the maximum temperature of the cycle, which is at the turbine inlet temperature, has a maximum value that it can apa tu bertahan, macam tu. Which is limited by metallurgical considerations. So many modern engine use air-cooled blades to permit elevated temperature. So it's possible to operate with uncooled blades up to about 1,000. So using these modern cooling blades, so we are able to use the turbine inlet temperature until around 1,300 or 1,400 Kelvin. And then at high temperature, it's necessary to extract air to cool both stator and rotor blades. The required blades may amount to 15% or more of the compressor delivery. Okay, so actually this bleed flow also will affect, okay, the overall gas turbine, the overall the overall performance of the gas turbine, because some part of the power produced by the turbine will be stator. This kat sini, the overall air cooling system for such unit is complex. Okay, this one. Okay, so it is accounted the value to denote these bleeds for cooling the disc, stator and rotor respectively. So we use this value like the efficiency, okay, beta, noted as beta for the bleed flow. Okay. Note that bleed acts to prevent the flow of hot gas down the face of the turbine disc. Okay, tak apa. Okay, so just want to give this expression. So if the airflow at compressor delivery is mass MA, okay, the airflow, the working fluid of the cycle engine, okay, then the flow available at the rotor is given by this expression. So instead of directly, if we don't take into account this bleed flow, then this mass flow MR will be directly equal to MA plus MF. But by considering this bleed flow, we need to take into consideration the value of this bleed flow efficiency. Okay, so the fuel flow is found from the fuel to air ratio required for the given combustion temperature rise and combustion inlet temperature and the air available for combustion. So the total overall mass flow rate throughout the cycle will be slightly changed due to this bleed flow. Okay, and then before this slide is an error, nanti saya cut. Okay, okay, I just want to show some of the example research paper study regarding the performance of aircraft or gas turbine cycle engine. So one of them is this one. It's an assessment of integration of organic rankai cycle concept for use in onboard aircraft power generation. So this one is actually okay. And it is a combined cycle. Okay, means that the Brighton cycle, the aircraft engine cycle is combined with the another thermodynamic cycle that is called organic Rankine cycle. It is this organic Rankine cycle is a thermodynamic cycle, normal thermodynamic cycle. So here, the idea is that an RC regenerator system can provide benefit when retrofitted, when integrated onto an existing engine and used to provide electrical power to the aircraft. Okay, so the idea, this is the, okay, this part is the ORC, organic Rankine cycle part. So this ORC has the main basic device components, pump, condenser, turbine and boiler, plus with a regenerator. So the idea is that they extract, okay, the heat, the waste heat exiting the between the turbine and the nozzle, okay, and use it to and exchange this heat, this hot fluid or waste heat from the heat exchanger before the nozzle. Okay, so this is the hot side of the fluid. Okay, and the organic, this one is the working fluid. Okay, will be the cold fluid. So the idea is that this waste heat from the heat exchanger, okay, will exchange heat with the organic fluid in the organic Rankine cycle within the boiler or evaporator, and this organic Rankine cycle will produce power, okay, extra power. Okay, so the mechanism is like the normal normal thermodynamic cycle. So from the boiler it goes to the turbine and condenser pump, etc. So ideally it will create power turbine here. Okay, so extract the heat from the heat exchanger, and this heat will be exchanged in the boiler heat exchanger, okay, with the organic fluid, as in cold fluid, and then use it to produce extra power that can be used to provide electrical power to the aircraft. Okay, but however, impacts on engine cycle design and size will also need to be assessed, need to be considered. Okay, so, but from this assessment, integrated of the organic RC with the cycles now, so they have a TSFC calculation, okay, performance calculation, thrust specific fuel consumption over the thrust value, but this is in a pound. Okay, so by adding the combined cycle ORC, organic Rankine cycle, they are able to reduce, but this is without taking into consideration the weight. Okay, they are able to reduce the TSFC, okay, lower the fuel consumption here. Okay, so this purple one is the base cycle without the ORC, and the red and green, okay, this part is the the ORC with the regenerator, okay, and bleed saving. So the TSFC is able to be reduced, okay, if they use integrate this concept. Okay, so this is one idea. And then this one is actually from the paper that I share with you about the heat recovery system. So I think this one you already seen and read. Okay, so this one is by adding recuperator and intercooler. Intercool recuperated turbofan engine. Okay, so you have the thermodynamic diagram here, enthalpy versus entropy. and the intercooler concept. So what are the major findings from this concept? Is that from this proposed design, the proposed systematic design method has successfully been applied to evaluate the heat recovery energy system. Okay, the evaluation has proven that the intercooled recuperated heat recovery system can bring benefits in turbofan engine design. Okay, and they also done the optimization analysis, optimize the intercooled recuperated turbofan engine has a lower overall pressure ratio, improvement of thrust, and around 10% reduction in the specific fuel consumption compared to the conventional traditional turbofan engine. Okay, so this is what the research has found, the study has found. Okay, by using the intercooled recuperated the extra heat recovery system into the turbofan engine. Other study, this one is okay, this one concerning it's kind of like the same as the organic Rankai cycle just now. ORC means by adding another cycle, combined cycle. So that's why it is named combined cycle. Another cycle which is a supercritical carbon dioxide. Okay, supercritical carbon dioxide. WHR is waste heat recovery. So the system of this supercritical carbon dioxide, the process, the system is the same as ORC just now, with regenerator. Okay, so the concept is that they integrate, okay, this supercritical carbon dioxide into this aircraft engine, between the low pressure turbine and the nozzle, and also before the compressor. Okay, so the thermodynamic cycles diagram, TS diagram of this supercritical carbon dioxide. Okay, you can see in the figure B. So so somehow the TS diagram will change. So the new concept for the propulsion system of long haul aircraft has been investigated. Okay, so the engine concept is based on a combined cycle configuration whereby the thermal energy of the exhaust of the gas turbine power a closed cycle CO2 waste heat recovery unit. Okay, so the mechanism, the idea is the same as ORC just now. Instead that here they use carbon dioxide at supercritical. Supercritical means that the pressure, especially pressure and turbine, is higher than the critical maximum pressure of the carbon dioxide of the fluid. Okay, so super higher above the critical point. So the idea is the same as ORC just now. So they extract, recuperate the exhaust heat, the waste heat from the exhaust, and this heat will be exchanged, transfer within the heater. Okay, within the heater of the CO2, the supercritical CO2, and this CO2 cycle will generate, produce a power. Okay, and then I think this is second last. Okay, this is concerning, okay, this is about biodiesel. Before I go to this one, I think I show the other slide first. Okay, this one, an outlook for radical aero engine intercooler concept. So again, using intercooler, by installing the intercooler at the engine. Okay, so a novel concept that use the rejected heat to generate additional useful power is then proposed. So again, a secondary cycle able to convert rejected intercooler heat to useful thrust is used to evaluate three possible scenarios. Okay, but I didn't show the three case here. But from these findings, the findings from this paper, from this assessment, As a final consideration, the gear intercooled engine cycle is re-optimized to maximize the benefits of the proposed heat recovery system, and the maximum SFC improvement for the three cycle by using the this intercooler concept. So the improvement of the specific fuel consumption is around 2% to 3% of improvement. Okay. So that is by using intercooler. And then back to this one. Okay, this one actually it's this idea actually not related to the modification of the cycle, but it is related to the by using biofuel, biodiesel, dual biodiesel, to increase, of course, the overall performance of this turbojet engine. Okay, the Aizan. So this paper is a part of Ezani, also is part of the team in that do this research. Okay, so they come up with a dual biodiesel blend. Okay, that can be used in this turbojet engine, uh, and can increase performance and reduce emissions. Okay. Okay, I think I stop here first. We have to take a break. Ada azan dah. So after this, after the break, we will continue with example. I will show some example of performance calculation. Okay, we take a break until around 7:30. Okay.
Okay, later.
Okay, we resume back our class. Are you guys, all of you are here, are back here?
Yes, Teh.
Yes.
Are you guys here?
Yep.
Ya,
Okay,
kita
oh,
ada Teh.
saya slow volume. Okay, okay.
Doctor, I just want to ask, what is the function of having a boiler in a system? Because I can't actually relate how the boiler can be in your system.
Okay, so boiler is actually the function is the same as evaporator. Okay, it's for gas turbine actually. Gas turbine power plant cycle. Okay, boiler actually usually related with the liquid, and evaporator is for gas fluid. So, but the function is the same. So evaporates the working fluid. But in aircraft engine, is actually this part is replaced by the combustion chamber.
Ah, okay.
Okay,
Alright.
just now maybe you saw from the other thermodynamic cycle, for example, the organic Rankine cycle just now, it use a boiler. So that boiler is for the is part of the that Rankine cycle, not part of the engine, aircraft engine.
Oh, okay. Understand. Alright.
Okay. So now, I want us to do together. Okay. As one example activity. Actually just to calculate the performance of a gas turbine cycle. So since you need to calculate, need to use some of the formulas. So I will give the slides to by WhatsApp group first. Later on, I will upload also in the Putra Blast. Just right now is for so that you can see all the formulas. Yeah, I download. Okay, I already send it to the on in the WhatsApp group. So that is the whole slide actually. Okay, so now in the slide also, towards the end, I have put this insert this example exercise uh, activity actually. Okay. So wait, share. I will also share it here. Mm, okay, this one. Okay. So in the same slide presentation chapter 2, so towards the end, around page 103, so you have this exercise. You can either look on the slides given that I sent you, or you can just look in this Google Meet. So this is the gas turbine example of a gas turbine cycle with a regenerator here. Okay, extra heat generator, and this is the compressor, turbines, etc. Okay, the normal. Okay, and then from here, from this simple gas turbine cycle, we have to evaluate the performance in terms of a specific work output, specific fuel consumption, cycle efficiency. Okay. So, with having the following specifications, so we have these values of the compressor pressure ratio, TIT, turbine temperature, compressor efficiency, turbine efficiency, the mechanical loss, okay, the mechanical efficiency is 0.99, combustion efficiency, the burner loss just now, 0.98, and the heat exchanger effectiveness. So all of those factors that we have seen just now. Okay, and then not yet finished. Okay, we also have some specification in terms of the pressure loss. So the pressure loss due to the combustion chamber, compressor delivery process pressure around 2%. Heat exchanger air side around 3%, the heat exchanger gas side 0.04 bar. Okay. The value given, okay, correct. 0.04 bar. Okay. Okay, and then ambient conditions, 1 bar, the normal ambient condition, and 288 Kelvin. Okay, so and you also have this figure, this diagram of the combustion temperature that you can use to find to estimate the fuel to air ratio in order to calculate the cycle efficiency later on. Okay, so first how are we going to start? Okay, you can look at the slides given, look at the possible expression that we can use first to specific work output. So basically, specific work output is the okay, it's the one here. Okay, the net work output of the turbine minus the work used in the compressor. Okay, I will open Jamboard so that we can like write on the board. Whiteboarding, start a new whiteboard. Turn link sharing on. Send. Okay. Okay. Okay, the link is there, but I need to change the access so that you can edit as well. Anyone with the link can edit. Okay. Okay. I think now it's okay. Okay, so we can edit the slides. This one. Okay. So, okay. You try to analyze to digest first. Analyze first the cycle, the problem given just now, and then try to think first on the how to evaluate the specific work output. I'll give sometimes. Okay. Later on, maybe I'll ask somebody to share, someone to share, and write on the whiteboard, Jamboard. Okay, go back to this slide. Try to copy paste the TS diagram so that maybe can see it better. Pressure loss, not this one. Boleh lah, this one. Boleh. Okay. Okay, so I copy paste the same thermodynamic cycle TS diagram. So we use this one numbering notation. Okay, so first part mana tadi? Okay, so okay, first part, maybe we can start from here. From point number one, from the intake at inlet. So point number one, we write it as TO1. So we assume that at the inlet it is we have ambient temperature at number one here. Okay, so the total one, so we use the total stagnation value instead. TO1 stagnation properties equals to TA ambient 288 Kelvin, and then the same for pressure will be also PA. Okay. Okay, so we will try to do from one point to another point. So even though the activity asks you to evaluate the performance of the cycle, the specific work output, cycle efficiency, etc. But usually for thermodynamic and propulsion cycle, we still have to solve it from the initial stage part, from the initial point, and then we go along until the end of the cycle. Okay, so so that's why we start with point number one, even though the question is to determine the specific work output. So first, number one, point location number one, settle. We have the temperature and pressure according to the ambient. And then next is point number two. Okay, the next point, number two, location means after the compression process, after the compressor. So so what can which expression we can use? Since we know the temperature and pressure of the first point, so we have to find a relation that links point one to point two. Okay, the compression process. So basically, we will use the equation. If you see from the slide, from the chapter slide, the one with the compressor efficiency, because it is given here the compressor efficiency. So we need to take into consideration that the efficiency. TO2 minus TO1. Okay, if you look at the slides, chapter 2, look at the equation 2.11. Equation 2.11, slides number 47. Okay, so we will use that one regarding the compressor efficiency. Okay, slide 47, equation 2.11, in the red box there. Okay, so if we copy the equation, so TO2 minus TA equals to 1 over TO1 kan. So TO1 is TA, compressor efficiency. Amirul Amin, yes. Yes, Amirul Amin, you want to ask something?
No. I thought it can.
Oh, okay. So we copy the equation 2.11, page 47 on the slide. So change the T O1 or total one to T ambient, because you already know the value of T ambient. And then okay, PO2 over PO1, so is PA. Ini gamma. So gamma here we use 1.4. We can take 1.4. And then minus 1. Okay, just copy from the equation. Okay, so from here, okay, so I think we have all the values. T8 ambient is 288, and the compressor efficiency is given. Compressor efficiency, isentropic efficiency of the compressor 0.85. And then the ratio of the PO2 over PA is the compressor pressure ratio actually. Okay, PO2 over PO1 ataupun PO2 over PA. So it is 4. And then gamma, we can use 1.4 and then minus 1. So we have, we can calculate the TO2. So TO2, okay. TO2, how much? And then from there, because since we want to determine the specific work output, so here we calculate next is the compressor work, the work of the compressor. Okay, so this one, ada tak dalam slide just now?
Doctor, what is the value for the ambient?
Given in the slide, I tunjuk balik. 288 Kelvin and 1 ambient just now dalam slide. This one. Okay. Ambient condition,
alright.
PA 1 bar
288 kilo
and
Kelvin.
PA 28 Kelvin.
Alright.
Yes. Okay, apa tadi? Compressor work. Okay, the equation is in the slide 77. We can use this one. Slide 77, because there is a mechanical loss, the mechanical efficiency. Slide 77, the work required to drive the compressor. So WC is CP equals to CP TO2 minus TO1, which is TA. divide by the mechanical loss. Efficiency 0.99. Okay, so CP here, we can use in kilojoule, so 1.005. Tak bagi okay, tak apa, saya bagi sekarang. So CP 1.005 kilojoule per kilogram. This is in kilojoule per kilogram per Kelvin. Okay, so that is WC. Okay, how much temperature just now you get? Maybe I ask Tengku Fawaz. Did you calculate this temperature?
Sorry doktor, tengah calculate lagi.
Okay, tak apa. Okay, you guys can calculate temperature and then compressor work. This is 0.99. TO2, we use this value that we get. Ambient is TA, ambient to 288 Kelvin.